Hello, doctor. I'm Tai Xiang, and my study focuses on machine learning for predicting personal loan defaults. In this section, I will discuss the introduction in conjunction with the background. The online personal loan market expands fast, while scattered personal credit data brings low risk control challenges. XGBoost and other ensemble models work well for risk prediction, yet most prior studies overlook the universal class imbalance problem in loan datasets. To fill this gap, my study optimized data pre-processing methods to construct an accurate personal loan default prediction model based on real banking data. Regarding the problem statement, the summary is that in actual loan scenarios, there will always be a majority class and a minority class in the datasets, and the models will be biased towards the non-default majority class, leading to bias. Most current studies focus on the improvement of the models themselves, while ignoring the processing in the pre-processing stage. Based on the preceding content, this study has three objectives. First, to identify key features. Second, to assess the effectiveness of the proposed balancing method, smooth SIGAN. And third, to determine the optimal combination of oversampling and ensemble model. There are four questions corresponding to the three objectives, with question 2 and question 3 derived from objective 2. In the literature review section, I identify four relevant theories, describe the development process of machine learning, and point out two currently popular methods for handling imbalance: oversampling, represented by SMOT, and generative, represented by GAN. On the left are some important references from the original text that I selected. In the literature review section, I finally highlight the research gaps. First, the feasibility of using SMOT SIGAN to balance samples. And second, the feasibility of combining this method with ensemble models in practical applications. As shown in the upper right figure, this study employs a general machine learning workflow, including input, processing, modeling, and output. This study used a real-world bank personal loan dataset containing 60,000 samples and 41 independent variables. This pie chart visually illustrates the imbalanced sample phenomena. As mentioned earlier, this study utilized three types of data: raw data, SMOT data, and SMOT SIGAN balanced data. Simultaneously, it employs three typical ensemble models: random forest, AdBoost, and XGBoost, ultimately forming a 3x3 comparison framework for as detailed a comparison as possible. Data processing is the core of this study, including data cleaning, data transformation, reduction, and imbalance handling. Among these, SMOT and SMOT SIGAN are the most important. Both are essentially about generating new samples. This study uses 6 evaluation metrics, among which AUC and KS are the most important. AUC reflects the model's overall ability to distinguish between default and non-default samples, while KS is widely regarded as a key risk assignment metric in credit modeling, used to measure the maximum separation between two types of predicted probabilities. Then the results are displayed. This table summarizes how I handle different types of row features. For data features, I converted timestamps and built a new feature called credit landmarks. Ordinal loan grids use numerical mapping, while unordered categorical features such as subclass, work type, and industry were processed with one-hot encoding. Work experience was transformed into continuous values for model training. All these standardized transformations guarantee valid inputs for my subsequent prediction models. In the data reduction section, the p-value indicates that recircle B is the independent feature and needs to be removed. However, the heat map does not reveal any quantitative features that needed to be removed. Overfitting is a prerequisite for evaluating a model. As shown in the table, pure smoke leads to severe overfitting with a large gap between the AUC of the training and test sites, ranging from 0.1128 to 0.1684. In contrast, smooth CGAN achieved a robust balance, narrowing the AUC gap to from 0.1030 to 0.1321, significantly alleviating the overfitting problem. This is one of the advantages of smooth CGAN over smooth. What is the optimal combination of oversampling and ensemble model? As shown in the table, random forest and AdBoost have low AUC and poor stability from 0.8095 to 0.8461, indicating weak discriminative ability. XGBoost consistently outperforms the other two models. The combination of XGBoost and raw data performs best with an AUC of 0.8661 and a KS of 0.5732, followed by the combination of XGBoost and Smooth CGAN with an AUC of 0.8653 and a KS of 0.5722. However, considering the bias of raw data towards the majority of samples, Smooth CGAN and XGBoost are the multiple combination. The results show that bankruptcy history, overdue payment records, and loan subclass are the most important predictors of loan defaults. The importance of bankruptcy history is 0.4224 in XGBoost and 0.0808 in Random Forest, both ranking highly. Overdue payment records have an importance of 0.0563 in Random Forest, also a key predictive feature. Loan subclass has an importance of 0.1442 in XGBoost, exhibiting high weight across all models. Now move to discussion organized around 4 research questions. For question 1, bankruptcy records, overdue history, and loan subclass are the top predictive features which proves past bad credit events dominate default risks. For question 2, Smooth can raise minority precision, yet triggers serious overfitting, leading to weak generalization on unseen data. For question 3, Smooth CGAN solves this flaw. It generates more realistic synthetic samples, lifting test site AUC and KS without sacrificing precision. For question 4, XGBoost paired with Smooth CGAN achieves the overall best results, with stable performance across AUC, KS, and precision. Finally, let's look at the conclusion, implications, and recommendations. First, the main findings. Loan data suffers severe class imbalance. Basic Smooth boosts precision but causes overfitting. Well, Smooth CGAN fixes this issue. The combination of XGBoost and Smooth CGAN achieved the best performance, and 3 credit indicators are the key drivers of default. Then, put forward targeted suggestions for 3 groups. For bank risk teams, they can apply the prediction framework and focus on critical credit features to cut losses. For data practitioners, SmoothCGAN delivers better generalization and regular model inspection is necessary. For regulators, unified standards for data processing and model governance should be set to support fair lending. That's all. Thank you for watching.